Now we have learned how to find the potential if we know the field. So using this relation, if you have the electric field in some region in space due to some source charge, then if you apply this integral, in principle you can find the potential difference between any 2 points. And this is what we have been doing. But you can use the differential form of this, either this way, so that you can find a relation to finding the field when you know the potential function. So if you know the potential function, you can find the electric field. And to see how is this, well, E dot dl is the change dv, which is the change, infinitesimal change in the potential as between 2 points separated by the vector, displacement vector dl. So this is dv, the infinitesimal change in the potential. Now E dot dl is actually E cosine theta dl, which is the component of E along the direction dl. So let me denote this by dl. So it says that the infinitesimal change in dv as you go a distance dl, the infinitesimal distance dl, is equal minus the component of the field along that direction, along dl, multiplied by the length dl. Now, if you write this in this form, then this tells you that EL, that is the electric field in a given region, is equal minus dV by dl in general. So this tells you that the component of the electric field in a given direction, along given direction, L, now specifies a given direction, is equal minus the derivative of the potential with respect to that direction. So for example, if your electric field was a function of r, of the distance, like in the case of a point charge, then in this case, the electric field at any point, at any r, you just take the derivative of that potential function by r and put a minus sign, and this will give you the component, the electric field, the radial electric field in this case. If your potential function was a function of x, for example, only, then in this case your electric field at any point in space will be given by the derivative of the potential function with respect to x. In general, if your electric field is a function of x and y and z, so it's a function of the whole space, then the component along x is found by taking the partial derivative with respect to x, the same for the y, the same for the z. The electric field vector now, which is now in three-dimensional space, so you have to write it as a vector, is actually given by this expression, and this is usually defined, if you are familiar with this notation, this is the gradient, is minus the gradient of the potential function. So the electric field is equal minus the gradient of the potential function. This checkpoint is an application of what we have just discussed. Try to think of it. Now, what we move back again to finding the electric potential due to charge distributions. So far, we have learned how we have derived what was the electric potential of a single point charge given with respect to V equals 0 at infinity. Okay, we have derived that expression, and then by using linear superposition, we were able actually to find the potential due to 2 point charges, 3 point charges, or n point charges. If you have n point charges, then to find the potential at some point in space, you find the potential of each of them, and then you add them up all together, and you get the potential due to this system of point charges at a given point in space. We have done examples about that. Now, what we need to do is, in reality actually, is to find the electric potential when you have not discrete point charges, but a continuum of charge. That is, the charge is distributed over continuously over a given region, just as we have done in the case of the electric field. So the charge might be distributed over a line, the charge might be distributed over a surface, the charge might be distributed over a volume. And this will be now your source charge, and you want to find the potential due to this charge distribution at all points in space. So what we do, again, it's exactly linear superposition actually. What we have done in the case of multiple point charges, the idea of superposition, we apply it here. And as you expect, this is your continuous charge distribution. Assume that it's distributed arbitrarily over any region, and you want to find the potential at this point P. What you do, you divide this mentally, of course, this whole charge distribution into small elements, dq1, dq2, dq3, n of them. So the whole charge distribution here is divided into small elements, dq. Each one of these now can be treated as a point charge because it's too small. Now, the potential of any one of them is that the potential of a point charge. Now, instead of the point charge, we substitute dq because the point charge now is this small charge element dq. Okay? So apply the formula for the potential of a point charge at a given point P. So for example, the first one of these dq will have its potential here will be dk dq1 over r1. For dq2, it's k dq2 over r2, and so on and so forth. Okay? Now to find the potential of the whole charge distribution, we assume that it's divided into n of these charges. Then we add up the potential of all of these dq's, and then take the limit as n goes to infinity, as we did in the case of the electric field. And this amounts to what? Amounts to integration. So actually, this is the expression for the electric potential of a continuous charge distribution. This is a formal expression, and the meaning of this is, again, just like in the electric field, divide the charge distribution to dq's, find the electric field potential of each of these dq at P, then sum all of these contributions in the limit and take the limit as n goes to infinity, or it means dq goes to 0, which becomes very, very small. Now, this is the meaning of this integral. Now, this is similar to what the argument is similar to what we did in the case of the electric field, except now that here we don't have any vectors because the potential is just a scalar, and therefore when you add up these, you are adding actually scalar quantities, and this integral is the integral of a scalar function. In the case of electric field, we had integral over a vector function. Okay, so it's much easier actually here to work out the electric potential. Now we will consider examples of different charge distributions, continuous charge distributions, and we will see how we apply this formula to find the electric potential in each case. How we do that? But before that, let me outline the strategy. Now, if the electric field is known in this charge distribution, you just, find the potential in that region. هاي آخر شيء اشطبيها، ما عملهاش معنا، ضلت بالغلط هاي يعني. أشوف. لا هذا شيء ثاني. اوكي هذا مهم. هلا بنرجع بنكمل. اوكي. بحكي لك لما نبلش، بس خليني اتذكرها هلا. Now, another situation where we have continuous charge distributions is that if we manage to find the electric field due to that continuous charge distribution, then using that electric field, we can find the electric potential. We will apply this approach later when we consider capacitance and how to find the capacitor. So, for example, we know this expression for the potential difference between 2 points, A and B, okay, which is this integral. Now, if it happens that your for example, you have a high degree of symmetry, okay, of the charge distribution, so that you can use Gauss law to find the electric field easily, then in this case you know the electric field in the whole space. So you can apply this relation to find the potential difference between 2 points, okay, in space. And then you set one of these to be you set the potential to be 0 at one of these points, and take the other points to be a general point. And so in this case you would be finding the potential in some region in space from the knowledge of the electric field. So this is an alternative approach to finding the electric field for continuous charge distribution when you have a high degree of symmetry that enables you to find the electric field. So you just integrate the electric field, and from which you can find the potential. As I mentioned, the main application of this is in the case of capacitors, and we will discuss examples later.